Welcome. A welcome for today's joint seminar between CGD and M-Cubed. I'm delighted to introduce Professor Dave Randall from Colorado State University, where he is a distinguished professor in the Department of Atmospheric Science. Dave will be speaking today about EarthWorks, a high-resolution coupled global storm resolving Earth system model with the purpose for both weather and climate applications. Dave holds a PhD in atmospheric science from UCLA. He has worked both at MIT and NASA before joining the CSU department. His current research is focused on modeling studies of cloud and their role in global climate systems using numerical simulation. He works on the development of improved cloud parameterizations, numerical experiments to determine the role of clouds in sustaining present climate and the role of clouds in climate dynamics. He has been a coordinating lead author on 2 of the IPCC assessments, one of which shared in 2007 the Nobel Prize, and has been presented out of Nobel Peace Prize, and has been presented with a multitude of awards, including the Jules Charney Award of the MS and the Creativity Award from NSF. For those virtually, I assume there will be a large crowd virtually. Please know you can go either to slido.com and look for CGD to post a question, or you can go to the link where it's being streamed, and it will link to that Slido question. So please put it there, and we'll answer questions at the end. Dave,
thank you.
Welcome.
Thank you. And I think I can tell the mic is working. So thank you all for coming. This is a project with participation by a lot of people, and I think I've got everybody here. Hopefully didn't miss anybody, but some of these people are in the room. So EarthWorks is a 5-year project supported by NSF Computer and Information Science and Engineering, SISE, to develop a global convection permitting coupled model, that uses a single, nearly uniform global grid for the atmosphere, ocean, sea ice, and land surface. And it's partially CESM based, so it includes the MPAS non-hydrostatic atmospheric dynamical core with a resolved stratosphere and mostly CAM physics. The MPAS ocean model, which I'll say more about here in a bit. The MPAS sea ice model, the land model, CLM, and the mediator, shown in the graphic on the side there, developed here at NCAR, and the community physics framework when it becomes ready. So that's our plan. The vision of the project is to, this is somewhat repetitive, but develop the capability to perform 3.75 kilometer fully coupled simulations using CESM as a base, partially explicit deep convection and gravity waves for both the atmosphere and ocean, actually, resolved stratosphere, and as I'll explain a little bit later, deep atmosphere capability, and a regional refinement option for both the atmosphere and ocean. Use the model with the 3.75 kilometer grid to study both weather and climate, as Judith mentioned, timescales ranging from days to decades. Use the model with the same high resolution grid to study deficiencies of lower resolution models with more parameterized physics. And that would be CESM, but also other models. And develop parameterizations that work well with both the high resolution grid and much coarser grids. And finally, use lower resolution versions of the model to study century scale climate change. So examples of goals, I don't want to spend time on this, but this is just to give an idea of what we are interested in doing, and I don't think it needs any explanation. Performance goals, and I'll say much more about this near the end of the talk, but our goals for the summer of 2025 with the 3.75 kilometer grid are to be able to run half a simulated year per day in atmosphere-only simulations with a resolved stratosphere, and one simulated year per day in coupled simulations with fewer stratospheric layers. I'm not going to give you a number. So this would be roughly like the standard CAM now, let's say. And this type of performance would be achievable only on a DOE leadership class machine, so not on Doreka or Cheyenne. So to run a model at very high resolution like this, you have to change things, and this is not bad, this is good. We should be changing things. So in particular, we need non-hydrostatic dynamics. We need optimal grids for the application, which I'll talk more about. We gain the ability to at least partially simulate deep convection for both the atmosphere and ocean and gravity waves. So I want to, before talking more about the model, I want to mention that Dave Williamson did very early work. I think this might be the first paper proposing the use of spherical geodesic grids for atmospheric global models. And the very first time I ever came to NCAR was for a meeting with Dave Williamson and Warren Washington. They were kind enough to spend an hour with a graduate student talking about global models. I remember that many years later. So the MPAS atmosphere has been developed by a team, of course, but led by Bill Skamrock, who is out of town today, unfortunately, and Joe Clem. And this is just the top page of their paper. There's some other authors there too. So this was published in 2012. And it uses a geodesic grid, about which I will say slightly more here in a minute, non-hydrostatic system of equations, regional refinement by grid spacing rather than nesting, and they have a deep atmosphere version under development. The MPAS atmosphere is the first global dynamical core developed in-house at NCAR since the Kasahara, Washington model, which was 50 years ago. So we're using the same grid for the atmosphere and the ocean. We're not going to do a mix of grids like what's shown in this slide. These are, of course, low resolution. We believe that although it can make sense, a lot of sense, to use different grids for the atmosphere and ocean with low resolution, it doesn't make sense with a grid spacing of a few kilometers or finer. So one grid to rule them all. Same grid for all components. It works well for the atmosphere, ocean, and land surface. And it has practical advantages. It reduces the operation count, less arithmetic, less message passing, and less memory needed. The ocean and sea ice models come from Los Alamos, as I said, and the papers that describe them are here. And one of the key people there was Todd Ringler, who for about 5 or 6 years was a member of my group at CSU before he went to Los Alamos. So a quick summary before we start to look at some results. A summary of simulations to date. There are a lot of words in this slide, but our philosophy here has been to start simple and go to more complex. So we started with low resolution AMIP and coupled simulations. And low resolution here means 120 kilometer grid spacing, then to 60, then to 30, and so on. I'll tell you more later. We have not tuned the model at all. Not because we don't think it needs to be tuned, but because, again, we're taking one step at a time. So we're currently using CAM6 physics out of the box, except for a few experiments that I'll mention. We've done aquaplanet simulations with all grids from 120 down to 3.75. We've done both AMIP and fully coupled simulations with 120, 60, and 30 kilometer grids, and we'll be doing 15 kilometers soon. Like I hope this month. We will also, and in particular, we're going to do a 2-year AMIP simulation on the 15 kilometer grid. And we have done 4 simulations with regional refinement, which I'll briefly talk about. So a few basic results. I have a lot of things to talk about here, so lots of triage on the slides. I started with about 120 and got it down to 50, okay? So I have to say something about the Earth radiation budget. So these plots show departures from observations and absorbed shortwave at the top left, outgoing long wave at the bottom left, and then the net at the top right. And there's a table listing the global means. The different curves are different grid spacings. Red is 30 kilometers, blue is 60, and green's 120. And so it's kind of interesting. As we go to higher resolution, the absorbed shortwave increases, but the OLR also increases, and the net doesn't change very much. In fact, if you look at the table summary down there for the global means, the net is smallest with 30 kilometer grid, but the others are getting big and the errors are compensating. So that's what happens. Annual mean precipitation, the top row is coupled and the bottom row is AMIP. And so one thing you can see here is that, well, the observations, first of all, the top left, so we're comparing with that, and generally the coupled simulations look a little more realistic than the AMIP simulations. But there are obvious issues. But you can certainly see the appearance of, high resolution features, for example, over South America at 30 kilometers that don't really show up at all at lower resolution. The NAO, the slide is from Jim Hurrell, who's here, NAO expert. So the top row is coupled. The top left is actually reanalysis. And the bottom row is AMIP. And generally speaking, the variability is in the ballpark of what's observed. The numbers at the top right show percent variance explained by the leading EOF. So I want to talk a little bit about weather research. Again, we envision both weather and climate applications of the model, and I'll say more about what I mean by climate applications in a few minutes. So first thing to get out of the way, we're using chem physics. Chem physics obviously is not appropriate on a 3.75 kilometer grid, and in particular, a parameterization of deep cumulus convection doesn't make any sense on a 3.75 kilometer grid. But we've been running it anyway, and so what you would like to think is that it goes to sleep. And you can see here that that's what's happening. On the right is global mean convective precipitation. The different colors are different grid spacings, and I see that somehow my legend disappeared. But as you go down there on the right, those are finer resolution. And so convective is a substantial fraction of the whole at 120 kilometer grid and becomes much smaller on the high resolution grid. That's not the only issue, of course, but it's good as far as it goes. So some results from a regionally refined Pacific Northwest simulation, and this is work done by Xinying Huang, whose picture is here. The little arrows up here show where the region of refinement is. Away from that region, the grid spacing is 60 kilometers, so fairly high. But it goes down to 3 kilometers here. And these are initialized from observations on October 1st of 3 different years, as it says down there. And so there are 3 cases. They're each 5 months long, and you'll see results from an average here on the next slide. So on the left are 2 observational estimates, and this is, you can see where we are, California, Oregon, and Washington. And then MG3 and MG2 are different versions of the Morrison-Gettleman microphysics. And then finally on the right is a simulation with WRF physics. And so the difference between MG2 and MG3, this is of course an Andrew Gettleman thing, but MG3 includes Graupel. And he says that most of the differences you see between those two are coming from the Graupel. So MG3 seems to agree better with the observational estimates on the left. than MG2 and also quite a bit better than WRF. Second case, and there's a few more things to show here. These are slides that I got from Bill Skamrock, and I'm sorry he can't be here. This is regionally refined over the central US, a little bit east of here, and was initialized using GFS analysis. And it's a case study of a squall line. So observed radar reflectivity is shown in the left panel, and then computed radar reflectivity, which of course involves a model of how the predicted microphysics would affect radar if there was a radar, is shown in the right panel. And so the right panel shows results obtained with WRF physics. And of course, WRF has been used for this kind of study for many years now. So that's a well understood model, and it's been refined to give a good result. And you see the strong reflectivity near the front or eastern side of the squall line, and weaker reflectivity associated with stratiform precipitation back toward the west. So the simulation is pretty reasonable. So here we have WRF physics repeated on the left for reference. You saw this on the previous slide. CAM6 physics with Morris and Gettleman 3, that's the latest version, in the middle panel, and then a modified version on the right. So let's talk first about the middle panel. You can see it doesn't look much like WRF or the observations. The intense precipitation is not occurring at the leading edge of the squall line. It's some distance back to the west, and the stratiform precipitation region is too big, much too big. So it's not a very good simulation. Bill Skamrock and colleagues have done some experiments and found that modifications to club, which is the turbulence parameterization in CAM6, lead to significant improvement. And I don't have time to really talk about what those modifications are, but you can ask me later or talk to Bill about it. They also got a further improvement by adjusting the microphysics, and what you're supposed to see here is that with the improved microphysics on the right side there, the cold pool, the density current, moving toward the right side of the panel is much better represented and more like WRF than it is in the middle panel without the microphysics mods. So the next case is Hurricane Maria. You can see where the refinement is in this case over the Caribbean. And this is the storm that devastated Puerto Rico, as most of you probably know. So it's a 48-hour forecast and a very strong hurricane during this time. So here we have observed brightness temperature from the OLR on the right side there, and MPAS with WRF physics OLR on the left panel. And you can see, the eye and the spiral bands and so on in both. When we go to CAM6 physics with MG3, we get the blue panel here, which doesn't really show spiral bands and doesn't look very much like the real storm shown on the right side. So something's wrong. Here's an experiment with modification to the evaporation, the same ones that were done for the Squall Line, and some changes. It says CPT changes. Those are coming from the climate process team led by Collins Arkiki at Penn State, who's modifying club friction in particular. And you can see some improvement, but there's still too much high cloud by a lot. So the fourth case, the last one I'll talk about in terms of regional refinement, is Western Pacific, and this again is Xingying Wang. The right panel there shows the high resolution topography used in the simulation. It's obviously very important in this part of the world. And this is a movie, so hopefully it'll play. The grayscale along the bottom is OLR, and there are colors you can see popping up in various places in the movie that go with the color bar on the right side there, and those are showing precipitation rate. So you can see tropical cyclones and other convective disturbances forming in here. Okay. So now I want to say something about climate-related research with the model. Now, there's an obvious issue with a very high-resolution grid like this. You can't do IPCC. You can't do CMIP 7, let's say. The climate is the statistical description of the weather. A key goal of climate research is explaining why the statistics of the weather are what they are. So a study of that type can be viewed as a climate study, and there are thousands of them in the literature. And I'm going to show you actually a couple of examples here. This is a very recent paper by, you see the authors. This is looking at results from Diamond, which is a intercomparison of very high resolution models of this type. And they're looking at deep convection and mesoscale convective systems in those models, in the Diamond simulations. And this is one figure from their paper. So I don't have time to talk about the details, but the observations are shown at the top for deep convective systems and a subset of those which are mesoscale convective systems. The paper describes the criteria for identifying the MCSs. But these are differences, so anything other than white is an error, essentially. Differences from the observations. And they make a comparison on various models. So the particular results shown here are for ICON, which is the Max Planck Institute / Deutsche Wetterdienst model used in Germany. So they're looking at the statistics of deep convection, and in particular, the statistics of mesoscale convective systems in places like North America, but all over the planet. Second example from Rios Barros et al., so this is NCAR, looking again at Diamond, and they're comparing parameterized deep convection with lower resolution to resolve deep convection. And this is just a summary of what they find. It's a figure at the end of the paper that summarizes the results discussed earlier. So with parameterized deep convection, they get a wider and weaker intertropical convergence zone. And you can see the momentum transport in the little curve on the left side there. That's the vertical transport of horizontal momentum, and it is essentially down gradient with the parameterized deep convection. With resolved deep convection, there's up gradient transport. Opposite sign, big difference. Not only that, but it's stronger. And the ITCZ is more compact or, better organized. So again, looking at the statistics of weather with a high resolution model without running for 100 years. We've done some work with a number of different machines, and in particular with a machine called Frontera at TAC. And TAC is NSF sponsored. It's a Texas Advanced Computing Center at Austin. And we were able to get some time under essentially to support their ongoing procurement, which hasn't finished yet. For a new machine, which is going to be called Horizon, which is mentioned there in the top line of text. And we were essentially obliged to do some calculations to support their procurement, to do some baselining. And so we're fortunate that our model was chosen for this. And that slide was actually slightly out of place. My fault yesterday afternoon, I was tired. But this slide should have come just before. We're going to talk about the computational side of the project now. So we're going to talk about throughput on GPUs and otherwise for that matter. So obviously a model with this very high resolution grid is aimed at for use on machines that have GPUs. And so we're looking forward to Dureco, and we'll be running on Dureco soon, I hope, maybe this month. we've made some estimates of throughput based on the assumptions that you see listed here. So a particular type of machine mentioned in the second line, and some assumptions about scaling based on Amdahl's law. And so let me just cut to the chase here. This is projections of acceleration. This is Frontera. This is the machine that we've been using at TAC so far, and it's a CPU-based machine. This is a machine like the Rayco, and the red dashed line that you see going across is half a simulated year per wall clock day, which is our target for 2025. And so you can see that the performance is much worse than that. It's taking way too many seconds per M-day, model day, on every row of this thing. So with a 16 times acceleration relative to this thing, we're still a factor of 2 or 3 too slow relative to our target. And so what we have to do to do is to optimize or omit some of the physics, in particular the deep cumulus parameterization will be switched off, and do more work to optimize the rest of the model, including possibly the coupler. The coupler is shown in red there. It's not a very big contribution, but it's a big chunk of half a simulated year per day over on the right. So we have work to do. This is the status of the GPU porting. So it's a complicated table, and no time to talk about everything, but we've got atmosphere, ocean, sea ice, subcomponents broken down then like dicor and physics for the atmosphere there in the second column, and particular pieces of the model. PUMIS is the microphysics, RRTMGP is the radiation, and CLUB is the turbulence, as I mentioned earlier. And so the programming model is listed there in the 1, 2, 3, 4, 5 in the fifth column, and optimization status is listed in the second last column, and then some comments on what we're currently doing in the far right column. So this is ongoing work, obviously. It's the nature of the table. So Frontera is the Texas machine. Rayco, of course, is the new NCAR machine. Perlmutter is a machine at NERSC in California, Berkeley, that is somewhat like Rayco is, I understand. Rich nod. Okay, good, thank you. And again, this table has a lot of information in it for a short talk like this, but there are timings and estimates of performance. And so on Perlmutter, on the far right there, the estimate is 0.146 simulated years per wall clock day on that machine. So again, we have a lot of work to do to get to 0.5. This slide is, and some of the others to follow, based on work by Sherry Mickelson. This talks about the need for the atmospheric science component of the project and the software engineering program of the project to actually communicate. And there are, in fact, frequent meetings, mostly virtual, that keep us in touch with each other, and it's all about communication, as she says here at the bottom. So technical challenges, there have been many, and we've overcome quite a few of them with help from a lot of people. We're facing some more now, and we expect to overcome them too. EarthWorks is trying to go to very high resolution, and there hasn't been a lot of work with CESM at that very high resolution globally. So we're running into issues that haven't been seen before because they crop up only with very fine grids. We're looking at weak scaling because we're interested in basically keeping the number of grid columns per node fixed as we add nodes, computing nodes, to go to very high resolution. So add nodes, add columns. And So in particular, you could compare performance with a 30-kilometer grid on 16 nodes, sorry, to a 3.75-kilometer grid, which is what, 3 halvings of the grid spacing on 1024 nodes. And looking also at memory scaling. One thing that we discovered at TAC is that when you run the model with a 3.75-kilometer grid, the startup, the initialization, before you actually start time stepping, takes about 45 minutes. That's not okay. We don't really know what the model is doing for those 45 minutes. During a lot of that 45 minutes, it's not actually reading data. Okay, so something's weird. And whatever it is works just fine at lower resolution, but it doesn't work for us. So that'll have to be fixed. Portability, so in particular support for multiple compilers. I'll come back to this, and infrastructure. So in particular, some bugs have been found going to higher resolution in terms of mesh partitioning. So creating, dividing the mesh up over the nodes. Software challenges listed here. One thing mentioned on the right there is that the models continue to change under us. So models, atmosphere, ocean, sea ice, and land surface, and they're all evolving, and our goal is to stay current with the evolving official releases of CESM as they go on a variety of machines and with a variety of different compilers and so on. So we are announcing today a functional release of the model. That means you can go out and get it. And Rich Loft predicted that somebody will do this while I'm talking, okay? We'll see. So functional delivery means that it works, it runs, but we're not guaranteeing that the atmospheric physics results are everything they should be. We're working toward that goal, obviously, but we're not there yet. So for today, 120, 60, and 30-kilometer grids are supported. The comp sets are listed there. So we've got fully coupled. We've got F2000, which is Data Ocean. We've got Aquaplanet and some other simpler things there. We're supporting the Intel and GNU compilers and AMD/Intel-based systems. We're projecting in the lower rows of the table a second release in a few months, July, that will include support for the 15-kilometer grid. The little red plus signs show what is being added. A new compiler and offload to GPUs. So the first release is CPU only. Okay. Third release for about a year from now, 7.5-kilometer grid, more offload to GPUs, and including the ocean at that stage, and some scalable diagnostic tools. And finally, July of 24, which is about a year before the end of the project, 3.75-kilometer grid and additional diagnostic tools. So it's an announcement and some goals. This is a summary of what's in the model. I've already said a lot of these things. And this is another sort of summary. Green means that it's passed the tests that have been done to confirm that it actually works. So Cheyenne and Gust are two machines that we've been on here. So Gust is the baby Dureco that's available now. And these are the different configurations of the model, including down at the bottom, fully coupled. So fail means it doesn't work right now. And so fully coupled is running on Cheyenne, but not Gust, and that's being worked on. And this is the same thing, but with a different compiler. I forgot to point out the previous slide was with the Intel compiler. Okay, so how do you get it? Here are the instructions. These slides will be available after the talk. in the PDF form. So here are the links. Somebody's furiously typing right now. And so there's an email list where you can interact with people and ask questions. There's a wiki page, and issues can be reported at GitHub as shown on the bottom there. So I'm at the end. Let me see the time. Oh, way early. I put the vision slide back up again just for symmetry. This is what we're hoping to do. And so a lot of the results I showed you today are weatherish results, but things like explicit simulation of non-orographic gravity wave drag is something that interests me in particular. And we can do that on the 3.75 kilometer grid, and we don't need to run it for 100 years, okay? So we'll be doing S2S type work, which is sort of in between weather and climate, and probably 1 to 2 year simulations with the finest grid by the end of the project. That's what I'm expecting. And this work on improved parameterizations that work with a wide range of grid spacings is of great interest to me personally, and I'm working on something there. And then, of course, the model can be run at low resolution, and so it's possible to use the same code and the same parameterizations to do much longer-term simulations of things like climate change. We are, as I mentioned, trying to coordinate with CESM, which is changing under us. We are engaging with CESM. I mean, my visit here today is an example of that. And with community scientists, we'll be at the workshop in June. And in 2025, when our NSF funding for the current project runs out, the current CESM leadership will decide whether or not to adopt EarthWorks as a supported configuration of the model. It's up to them, and we hope that they will, but we'll have to wait and see. It's going to depend on what we can accomplish between now and then, obviously. So concluding remarks, just a kind of very coarse summary. The model's running, and we're doing a functional release today. It took about a year to get the ocean model to run inside CESM, making, obviously it was working for DOE, but we had to incorporate it into the CESM framework, and there was a lot of work, and this was Don Daslick who did most of that, down in the front row here. I showed you that the deep convection scheme in Camp 6 goes to sleep at high resolution, and our intention is to switch it off, and that'll obviously speed the model up a bit. But running the model at, let's say, 15-kilometer grid, you probably want it on, and we'll be doing experiments. And we intend to develop something better. I showed you that we've run into issues with club. Those are being worked on both at M³ and actually at CSU and at Penn State. So work is ongoing, and Vince Larson is in the loop. But we don't have a solution yet, although some tests look promising. Porting to GPUs is well underway. We started, of course, with the MPAS atmosphere dynamical core already running on CPUs, thanks to a collaboration between NCAR and IBM some years ago. And DOE had already gotten the ocean model running on GPUs. So we had a leg up at the beginning. And a lot more has been done since then. So the next thing to be running on CPUs, we think, or GPUs, we think will be club. And there's a prediction that that will happen around the end of this month. So we'll see. But, it's starting to look like it's within reach. And again, our goal is to produce half a simulated year per day on a 3.75 kilometer grid by the summer of 2025. And we'll see. That's it. Thank you.
Okay, thank you to our speaker. So Nick, if we could switch it over to see some of David's colleagues who will be joining us for the question, answer, and discussion session. But now I'd like to open it up to see if there are any questions in room. And again, if you're watching virtually, you can go to the Slido link at the bottom of the YouTube page to put your questions into our chat, and we'll take those alongside the in-person ones. Okay, Adam.
Back row, of course.
Yeah.
Thanks for that. My understanding, and Go can correct me, is that near the end of 2024 is when we're planning for a new CSM3 release. And looks like you're planning on sort of keeping the CAM code base you're working with sort of dancing with us up until the end.
That's the idea.
But you're probably not going
Takes two to tango.
But you're probably not going to switch over to our new 58-level vertical grid comprising our new...
Actually, we are planning to use at least 58 levels. We're going to resolve a stratosphere, and you know, I've been analyzing some work done by Isla and Yaga recently that uses, I think it's an 83-level model version of CAM.
Isn't there a lot of tension with getting that 0.5 simulated year per day?
Yeah, that's right. Yeah. Okay. On the other hand, you know, adding levels doesn't introduce any more message passing. It's all in the node. So, we'll see what we can parallelize within the column.
Okay, thanks for clarifying that. Rich had a question.
Oh, yeah, go for it.
Do you have a river routing model, and what grid does that run on? And similarly for waves?
Yeah, well, okay. River routing and waves are two examples of things that we decided to sort of hold at arm's length. They were not goals when we wrote the proposal in 2020. We're not introducing a new model. I mean, I don't know whether Mozart will just translate directly to the 3.75 kilometer grid, but our goal would be to use that or something closely related to it. So you asked about river routing. What was the other one? Waves. Oh, waves. No. Well, okay, it's on the list, but not high priority at this time.
Okay, and I'm going to switch to a couple of the online questions. So Trude would like to know, for the Squall Line case, what was the improvements that were made to the microphysics?
The main improvement was increasing the evaporation of precipitation. And I don't know any more than that. I can't give you a more detailed answer. It's an Andrew Gettleman question.
Yeah, just responding to the river thing quickly before a question. We're actually trying to work towards another model called Mesorat, which is not a grid-based model, catchment-based model, sort of vector-based, which can scale across resolutions much more readily than Mozart can. So,
thank you very much.
If that works out, then that's great. It might slide in well. I guess I have sort of two questions. One is I'm trying to understand the scale of the effort. Like how many? Just trying to understand how much work this is. How many people are like directly working on this at CSU or NCAR or elsewhere?
Well, okay. I think the breakdown of the funding is 60% to CSU and 40% to NCAR. So EarthWorks is paying some salaries here at NCAR, or partially, and some people at CSU, but not so many, as you see listed here. And we've been fortunate to have a lot of participation, a lot of help from people who aren't getting paid to do it. So we see that as a good thing. It's a sign of support. We are thinking about, you know, writing some more proposals that would allow us to fund some more things, but that's where we are right now.
And then a follow-up is not really related, but is, you know, the international community is working on this, right? You mentioned ICON.
Yeah.
Are you experiencing any sort of collaborations or interactions with the international community that's sort of helping you understand things, or are you finding that the challenges within CSM are just sort of, unique and each group is finding unique challenges, or is there some sort of cross fertilization?
So far, we're buried in the practical work with CESM, but you mentioned ICON. I'm particularly interested in that model. I've had some interactions with Max Planck in the past, and I was on Bjorn Stevens' PhD committee, actually. So our model, like theirs, uses the same grid for all components. I think it's the closest analog, and it's in Europe. So we certainly intend to work with them. I'm giving a talk virtually at EGU sometime soon, and there's an ECMWF workshop coming up that we will probably go to. And we're also interacting with the group in Tokyo. Okay, so we're trying to plug in internationally, but up to this point, we've been pretty busy just trying to deal with practical issues to get as far as we've gotten in 2.5 years.
Okay, thank you. Apologies, Helen, if I get this wrong as an acronym, but online would like to know, your slide has data assimilation with an NUOPC cap. Do you have an NUOPC cap for DART or plans to implement this?
We have new OPSI caps, yes. That was a big part of the work that was done by Don at CSU to get the ocean model working. We are interested in data assimilation, but we're not trying to do it. What we'd love to have is a collaborator doing that, and I hope that'll happen.
Okay, thank you. And then we have a couple questions from Peters, and then we'll get to Judith.
Thanks, Dave. This is an incredible project. I'm going to be that person who asks, how does this tie in with SEMA and all the efforts that are happening now at NCAR?
Well, that is a charged question, obviously. SEMA and EarthWorks are not the same thing. SEMA is nominally at least atmosphere only. It's an internal NCAR project. EarthWorks is a university-based project, so they're distinct. We're both using the MPAS dynamical core, and we're able to, so EarthWorks is able to benefit from some of the tests that SEMA is doing. There's certainly a synergy there, but there's no formal connection. Does that answer your question?
Yeah, thanks.
Okay. Hi, Peter.
Hi. So you mentioned ocean component from 120 kilometers down to 3.75.
Well, yes, I know.
So are you using the same parameterizations across all those resolutions?
We're using Gent McWilliams, yes, all the way. And that 120 is too coarse, I know that, but we're just sort of working our way to higher resolution, as I told you. At very high resolution, Gent McWilliams is not appropriate anymore, at least that's my understanding. So it's another example of something that could be switched off. And, so maybe that'll help us.
Okay. Oh.
In fact, Phil Jones has suggested things that
You need the microphone.
Yeah. Phil Jones has suggested to me things that will be switched off once we get to beyond the 30 kilometer. At 15 kilometers, I think we'll be starting to switch some of those things off.
Yeah.
Okay, and Jimmy Dudia online had a related question about the ocean. So for the ocean, is it the same grid? And if so, are there any partial ocean points?
It is exactly the same grid. I don't actually know the answer to the second part of the question. Anybody else know? Don, are there partial ocean points? No. Okay.
Okay, and the answer to that, Jimmy, if you didn't hear it, is no. No partial ocean points. So Judith?
Thank you very much. Very interesting. My question is about the GPUs. MPAS there's a version of MPAS on GPUs. Are you planning to put the ocean on GPUs?
Yes.
And what's the timeline for this? And also, will putting it on GPUs still be able to update the model, let's say, to the latest CAM version, or is it once it's on GPUs, it's sort of a one-way road? How is the plan?
Well, there are several pieces to that. As far as the ocean is concerned, yes, it runs on GPUs, although we don't have much experience with that yet. But DOE has done the porting, so that's done. I believe the sea ice model is not yet ported to GPUs. For the physics, let's take an example. Club is being ported to GPUs in such a way that it still runs on CPUs. Okay, we're using OpenACC currently. And so we're not breaking it. The new radiation, RRTMGP, it runs on GPUs, but it also runs on CPUs. So there shouldn't be any issue there. Rich?
Oh, hold on one moment.
Hi, so yeah, the way I would just amend what you're saying is that all the examples that Dave just cited, there's engagement with the ongoing development efforts in all of those. So we're working with the RRTMGP integration with Brian Medeiros. We're working with the PUMAS development to keep that code current. So in other words, every time it gets modified, we want to have in the repository the OpenACC directives carried along as that gets integrated. Same thing with the DI core with Michael Duda in MCube with that. And what's the club? Well, you mentioned that there's engagement with club. And an example of club is kind of interesting because we expect to see vectorization on CPUs becoming one of the side benefits of getting it to work on GPUs. So there should be better club performance within the CPU code because of that effort as a side effect. But the key thing is to work with the people who are modifying the repositories, or you'll forever be playing a pursuit curve. And that's something that requires a lot of dedication from both sides too.
So as one of the slides mentioned, communication is key, and there's a lot of ongoing communication. We know these people, they know us, and we're working together.
Okay, thank you. Oh, yeah, Laurent.
A question regarding the tuning of the model. So what kind of strategy do you have using, low resolution to inform high resolution, maybe emulators, PPE type of experiments? Do you have any thoughts about that?
The best answer I have for you is that regional refinement gives us a way to tune relatively inexpensively. We're not going to be using an ensemble of 100 simulations with regional refinement to do tuning, but we'll have to do it the old-fashioned way.
Okay, thank you. And are there any more in-person questions that the audience might have? All right, well, if not, we're coming at the end of the hour, so why don't we thank our speaker one more time?
Thank you.